All right, welcome to AQA AS Chemistry, Paper 2, Organic and Physical Chemistry. And this is the 2022 paper walkthrough. Time allowed an hour and a half. If you check out the link, you'll find a copy of this paper or the link to this paper in the description to this video. And yeah, you could have a go at it first, or you could go question by question or work through as we go. All right, let's get into it. This question's about rates of reaction. Potassium manganate 7, KMnO4, reacts with sodium ethandioate, and that's Na2C2O4, in the presence of dilute sulfuric acid. 2MnO4 minus, AQ, plus 16H plus, hydrogen ions, AQ, plus 5C2O4 2 minus, AQ. With the arrow goes to 2MN, 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 2 plus AQ plus 8H2O in liquid form plus 10 CO2 gaseous. The reaction mixture is purple at the start and goes colorless when all the MnO4 minus aqueous ions have reacted. The rate of reaction can be measured as 1000 over the time, where T equals the time taken for the mixture to go colorless. A student investigated how long it takes for this reaction mixture to go colorless at different temperatures. The same concentrations and volumes of each reagent were used in an experiment at each temperature. Table 1 shows the results. So we have the temperature here, and the range of our temperatures goes from 32 to 38 to 44, 54, and 67. And then below that is the time for each, which is 155, 85, 50, 22, and 9. Now, at the bottom, we have the rate of reaction, which has been measured by doing the calculation 1000 divided by T. And we have 6.45, 11.8, 20, and 45.5. And we have the final rate of reaction missing for the result at 67 degrees. So the first question says complete table 1 for 1 mark. What we need to do here, okay, is simply write 1000, and I'm sure all of you can get this right, and divide this by T, and T in this situation is 9. So we want to do 1000 over 9, and that's at the temperature of 67. And when we plonk that into the calculator, we get an answer of 111.1. So you could leave it as 111, 3 significant figures, or you could leave it as 111.1. The next question says, state the independent variable in this investigation. When we scan read through here, we're looking for what are they actually changing. And of course, you can see here in the table, the temperature is changing. And here it even says a student investigated how long it takes for this reaction mixture to go colorless at different temperatures. So what the experimenters are changing, or the student is changing, is the temperature. So that is the independent variable. And just for your own knowledge, the what are they recording is the time taken. That would be the dependent variable, but they haven't asked us for that. So 1.3, the student noticed that the temperature of each reaction mixture decreased during each experiment. Suggests how the student calculated the temperature values up here in table 1. So what they're saying is that actually where they've got this first temperature recorded at 32, instead of them setting out to record it at 32, they might have started at 35. And then during the course of that reaction, which took 155 seconds, the temperature dropped from 35 to 32. So they're asking, how did they decide which temperature they should put for that reaction? Was it 35, 34, 33, or 32? Well, the best way to do this, how they should record it and how they probably recorded it, was record initial temp. You should write the full word temperature, but I'm trying to save time. And then record final temp, find mean temp. So you're going to record the final and initial temp and then find the mean temperature. Alternatively, they could have kept the temperature the same if they used a water bath. So as an alternative answer, which means the temperature, if they set it at 32 degrees, it would have stayed at 32. Alternatively, use a water bath. And if you do that, the temperature will remain the same throughout the course of the reaction. Okay. Question 1.4. Use the data in table 1 to plot a graph of 1000 over T against temperature, and that is worth 3 marks. You can see here I brought the table over and copy and pasted it here. Otherwise, we'd have to be flicking back and forth, which is always annoying. So on the y-axis, we have 1000 over T, and on the x, we have temperature. So the first thing to do, which is going to score us the first of these 3 marks, is to plot the values on the y-axis. So we're looking to put 1000 over T, which goes from 6.45 up to, what was our answer to the first question? It was 111. So we want to go up to encompass at least 111, and we'll probably find the best way to do this is to go up in 20s. If we go up in 10s, we're only going to get as far as roughly. Yeah, we go up to 120. If we went up in 10s, we'd only go up to 60. So we wouldn't cover all the data points. Of course, I need 0 as well. So that's our 1000 over T there. And now what we're looking for is that will give us 1 mark for the axis, even though mine aren't very straight. The next point is to plot the points. So let's get that on for the next mark. So 6.45 and 155. So we want to go. Now, you are allowed an error of like half a square. So if we go to temperature 32, and now the temperature along here is 10 small squares. So 32 is 2 squares along. And we want to go up to 6.45. Now that's 10. So we're really coming down to the halfway between these would be 5 when we're erring towards there. So there's my first point. Now 38 and 11.8. So 38 is 2 back from 40. And then I'm going up to 11.8. So that is 10. 11.8 is almost 2 squares up. So you could pretty much put it 2 squares up because you're allowed 1 small square to be, or half a small square out. So the next one is 44, and we're looking at 20. So this is 45 in the middle here. So we just want to go back 1 and go up to 20. And then we've got 54 and 45.5. So we want to go to the middle here to 54, go back 1 again and go up until 45. So here's 40. And we know that the middle line is 50. And we want 45.5. So almost bang smack in the middle. Again, half a square out is not going to penalize us. So we're going to be all right. And then the final one is at temperature 67. So that's 3 back from the far side, which is 70. So we want to count 3 mini squares back. And we're looking for 111. So we're going to count 3 squares back, and I've gone up to 100. This is 110. So I don't even want to go a full square up because I could leave it at 110, but let's go 1, 2, 3 in and up a little. There we go. So there's our points. Now that is going to get you your second mark. Now, what I can't do very well on here, I wish I could, but I can't, is to draw a smooth line through these points. So you don't come from 0 with this line. You just want to create a smooth curve. And you don't want to take your pencil off, and you don't really want to stop, especially on the computer like I have. And you've got to kind of aim. Now, again, they allow some leeway. So they will allow you to miss those points by 1 small square. So you can miss the point by a small square, but it should be, you can see here, I've missed this second point here at the temperature of 38. Over here, I've missed that point, but it doesn't matter because I'm within 1 small square of the line. Now, obviously, my points have disappeared, but we know they were roughly in the correct place. So that's all 3 marks for the curve. The next thing we want to do is say, use your graph to find the time taken for the mixture to go colorless at 60. So what we're looking to do here is draw a line going up at 60. So we're going to draw a line going up at 60 to meet our curve. And then we're going to draw a line going across. That is like the worst line going across. So it's about 64. Let's just double check that because my line don't look too great. Yeah. As long as they're going to be pretty generous here, as long as think I need to shorten that original line, as they're going to be pretty generous, basically. As long as you have indicated on your graph your value, they're going to see, can you work it out from your value? So we know that mine looks like 62 now. So I'm going to do 62. You could have 64. It won't matter as long as that is the value you've shown on your graph. So 1,000 over 62. No, that is all wrong. We want to go equals the time. So what I've done here is I've basically rearranged. That would have been 1,000 over t equals 62. So I can do 1,000 over 62 equals t. And that is going to give me roughly 16.129. And I'm going to just put that to 3 sig. So I'm just going to put 16.1. Beautiful. Right, 1.6, the investigation shows that increasing the temperature causes the rate of reaction to increase. Explain why a small increase in temperature causes a large increase in the rate of reaction. When you're trying to increase the rate of reaction, of course, catalyst, surface area, concentration, temperature, pressure, etc. Temperature has a huge effect on the rate of reaction, and it's a larger effect. And it's because it kind of increases the rate of reaction in a twofold way. So first of all, it increases, I'm not going to write the full word, but you should, kinetic energy. Of the particles, or you could say, if you want to be exact, it increases the average kinetic energy or the mean kinetic energy of the particles. What does that mean? So they're traveling faster, so you could write that, or you can just write more collisions, and you need to say per second, or this means the same thing, but increased frequency of collisions. By saying collisions per second is the same as saying increased frequency. So you could say either of those, and that is going to score you a mark. And the second way that it increases the rate of reaction is that particles have, and this is a shorthand way of saying more than, you can draw, particles have energy greater than the activation energy. So more particles have energy, I should say more particles, not all of the particles have energy greater, otherwise they'd all react at the same time. So more particles, or a greater proportion of the particles, have energy that is greater than the activation energy. So that is our second one. So temperature increases the proportion of the particles, or sorry, increases the amount of the particles. I'm using the word proportion incorrectly there. It increases the amount of the particles that have energy greater than the activation energy, but it also increases the frequency of collisions. So it's got a twofold attack on increasing the rate of reaction. And that's the end to the first question. How did you do? Check it out, a 9, etc. Blah de blah. Let's move on. Okay, here's question 2. A student has samples of these 4 compounds, but does not know which is which. We've got butanoic acid, 2-methyl-propanol, aldehyde, 2-methyl-propanoic acid, carboxylic acid, 2-methyl-propan-1-ol, alcohol. 2 of these compounds can be identified by simple chemical tests. The other 2 compounds that contain the same functional group, that's our butanoic acid and our propanoic acid, hopefully you've spotted that, they've got the same functional group as each other. They can be then distinguished by a spectroscopic technique. Describe how these 2 steps could be used to identify which compound is which. So first of all, we need to say, how would we identify each compound? So I'm going to start with, could really start anywhere, but let's crack on. 2-methyl-propanol is an aldehyde. Do you remember the test for aldehydes? Well, one of the tests for aldehydes, we could use Tollens reagent. And so straight away, I'm going to get a mark for saying, hey, use Tollens reagent. Now, what's the positive test? If aldehyde, it gives a silver mirror on the inside of the test tube. So that I've given the positive result for that. So that's one way I can find out that I have 2-methylpropanol. It's the only one of those 4 that will give a silver mirror. Now, I could use, God, I can't spell this properly, Fehling's reagent. Fehling's will give, gives a orange red or red orange precipitate. So if I don't want to, I like to use the Tollens and the silver mirror, sticks in the head more. Fehling's is very similar to sort of copper sulfate when you do the Benedict's test in biology, but it goes red orange with aldehydes. Now, how am I going to identify the alcohol? Methyl propan 1. So methyl propan 1-ol is an alcohol. So I can use potassium dichromate. And that's potassium dichromate 7. Okay, so I can use potassium dichromate 7, and it's going to go orange to green. Okay, so that will go orange to green. So again, I'm going to pick these marks up. However, it's not the only thing that goes orange to green. Alcohol. The aldehyde is going to go orange to green as well. So what we're going to need to do here, as aldehydes, quick note, aldehydes also give a positive test. So make sure you do the silver mirror tests first to rule out aldehyde. So if you do get an orange to green, it could be an alcohol or it could be an aldehyde. So we want to rule out the aldehyde by also doing the silver mirror test and only then confirming that that is the alcohol. Now, to distinguish between the carboxylic acids, so to distinguish between the carboxylic acids, we're going to use, you probably guessed, infrared spectroscopy. And we could just say that, and that would get us 1 mark. Use fingerprint regions, so they're regions which identify specific molecules. So you can just say, and look at the fingerprint regions. Or you could have a data book, or you could say compare to a data book with different carboxylic acids IR spectrums. So you could have known spectrums of different carboxylic acids like ethanoic acid, propanoic acid, butanoic acid. And when you compare butanoic acids to all those, you'll notice it matches up. It will be the same as the one in the data book or very similar. So you could say that compared to known infrared spectrums. Right, let's move on. Question 3. This question is about isomers. Hex2ene has the molecular formula C6H12. Draw the displayed formula of a position isomer of Hex2ene that exists as an EZ isomer. Now, position isomers mean we're going to move the double bond from the position it's currently in. So we want to move that double bond and find a positional isomer that can have form EZ isomers. So first of all, I'm going to look at Hex1ene. So let's take a little check at this, guys. This may be where all our answers lie. So let's do Hex1ene. That's me just moving the double bond of the Hex2ene 1 along. I've done too many bonds. Always count around your carbons. Make sure you only have 4 lines. You should know that. Carbon's group 4. So this is hex 2E. Now, when I look at this, I haven't bothered drawing on all the, but straight away, what's the issue I have here? This double bond here cannot do EZ isomerism. Why, you say? Why? You can only do EZ isomerism if you have different groups attached to each of the carbons on the double bond. If we call this carbon 1 and carbon 2, well, carbon 2 is good to go because it has 1, 2, 3, 4, a butyl group attached and a hydrogen. So that would be good to go. But unfortunately, it can't do EZ isomerism because on carbon 1 here, we have the same identical group. So you can only do EZ isomerism when the groups attached to each carbon are different. And we're talking about the carbon on the double bond. So the double bond carbon, each one has different groups attached. Super. We can't look at hex 2ene, so the only other one we can look at is hex, we can look at like hex 3ene, and that will be a positional isomer. So let's check out hex 3ene. So we can't do hex 2ene. There are some other ones we can do. So, but let's check this out. So, I think that's right, guys. I think that is right. But we shall see. Let's put that there. Put that there. Boom, boom. I'm not going to draw the hydrogens. It's too long. Right, now if we check this, has this got 4 different groups attached? I'm going to circle them in green. So carbon 1 we have and carbon 2. Let's look at the groups attached to carbon 1. I'm going to have a hydrogen here and I'm going to have an ethyl group here. And then on carbon 2, I'm going to have a hydrogen there and I'm going to have a ethyl group there. So this can do EZ isomerism. The reason it can do EZ isomerism is because each of the carbons has 2 different groups attached. See, the groups aren't identical to each other. So perfect. Right, the next question is, so hex 3ene is your answer there. You want to be drawing that. Make sure you include all the hydrogens. I'm being lazy. Draw the display formula of a chain isomer of hex 2ene that does not exist as an EZ isomer. So it doesn't exist as an EZ isomer. Now I'm looking at a chain isomer. That means I can't keep the hex in the name. I can't keep it as a 6-carbon chain. I have to change the length of the chain. Hence the name chain isomer. So what I'm going to go for here, simply when you want to change the length of a chain, just bring it down 1 and add a methyl group. So I'm going to go for 5 carbons in a row, like that. So we now, instead of hexene, we've now got pentane, but I need to add a double bond in. So let's keep it in the same position. So we've got pent 2ene here. Now, how am I going to chain isomer this bad boy? Well, I can't really. Let's add 3 hydrogens there. Then we're going to add a methyl here. Now you should see the problem straight away. Why can this not be EZ? Look what I've done to carbon 1 and carbon 2. Okay, so if I add the hydrogens in, this will probably make, I'm going to be boring and add all the hydrogens in. Bear with. Okay, so I've got all my hydrogens. Not quite yet. Hydrogens are in. Now look at, I should have written carbon 1 and 2 in a different color. There we go. So we've got carbon 1 and carbon 2. Now, let's have a look here. Carbon 2 is good to go. Carbon 2 has an ethyl group and a hydrogen. So you're almost thinking this can do EZ. But look what I've done here. I've attached. If you want to make something that can't do EZ, just make sure you attach 2 identical groups to one of the 2 carbons with the double bond. That cannot do EZ isomerism. So this is my isomer. Super. 1, 2, 3, 4, 5, 6. Yeah, we're all good. Let's go. Next question. Butanal has the molecular formula C4H8O. Draw the skeletal formula of a functional group isomer of butanal that has an absorption range of 1680, 1750. Right, if you go to your data book and you look here, you'll see that this is going to be, we're going to draw a ketone here. We're going to get this carbonyl group and we're going to draw a ketone. So if we want to do a functional group isomer from butanal, the aldehyde, we just move that C double O bond into the middle and it becomes butanone, butan 2O. And there you go. Question 3.4, draw the skeletal formula of a structural isomer of butanal that has an absorption in the range 3230 to 3550 in its infrared spectrum. So really, once you consult your table with all the different ranges, you'll find that there's a stretch for the OH bond here. So we're really looking for, let's put that in capitals, we're really looking for an alcohol. Butanal, we need to probably work out butanal's MR. That will help us. So if we quickly draw out butanal, you should be able to do this. The but means that there are 4 carbons. Quickly draw out the hydrogens around it like this. Remember, it's an aldehyde, so it has this carbonyl group and then just a hydrogen off there, and that makes those 4 bonds around it. We need to work out the molecular mass of this. So you're looking at 4 times 12 for the carbons, and that's going to give you 48. You're then going to add up all the hydrogens. So we've got 1, 2, 3, 4, 5, 6, 7, 8. So we got 8 for the hydrogen. So we add those two together. It's going to make 56. And then we've got to add the oxygen on there. And of course, oxygen is 16. Whack those together. And we have an MR for butanal of 72. So really, we're looking to draw a molecule that has an OH group attached and an MR of 72. And that's really your only restrictions. There is a whole range of molecules you could draw. You could draw this little bad boy here. There's a whole range of different ones you can draw. Of course, if you check the mark scheme in the link in the description, you'll find that as well. So we could add a double bond in, and we could draw an OH over here. Double bond there and another OH. There's a whole range, but your restricting factors are it needs to have a molecular mass of 72 and an OH bond, because that's where we've had this stretch where there's been an absorption in the infrared spectrum. Okay, let's move on. Well, I'm going to actually clear some of that because that's going to interfere later on when I do the other question. That was just showing you how to check the MR of butanal so you'd know whether you've got it right or not when you draw your isomer. So let's look at 3.5. Several saturated halogenoalkanes contain 17.8% carbon, 3% hydrogen, and 79.2% bromine by mass. Calculate the empirical formula of these compounds. Give the IUPAC names of 2 saturated halogenoalkanes that have this empirical formula. Okay, so all we need to do here is do an empirical formula. You've done these at GCSE. So I always just pretend these percentages are grams and like you're doing a mole calculation. So we want to do 17.8 over 12. Then we want to do, that's the 3% over 1. What is the 1? The 1 is the atomic mass, the AR of hydrogen. The 12 is the AR of carbon. So this is my carbon. This is my hydrogen. It's good to label these so you know what you're doing. And then we've got the bromine. We've got 79.2 of bromine. God, I've got to look in my periodic table. I can't think offhand. What is the AR of bromine? Pretty much 1 to 1 here, 79.9. Okay, now we work those out and we're going to get 1.48 rounded in your calculator. Then we're going to get 3. And then we're going to get 0.99. Okay, close enough to 1. Now what we want to do is we want to get these into whole numbers, ratios. We don't want this 1.5 business. So we're going to multiply these roughly by 2. And that's going to give us 3, 6, a little bit of rounding, and 2. So our empirical formula is going to be C3, H6, BR2. We couldn't leave it as 1.48 because we can't have 1.5. We have to put it into a whole number multiple, the simplest whole number ratio of elements in a compound. That is your empirical formula. Now, can I divide this by 2? No, I can't simplify it anymore because that 3 won't divide by 2 and that 2 won't divide by 3. So that is my simplest ratio. The next part of this question says, give the IUPAC names of 2 saturated halogenoalkanes that have this empirical formula. Well, if we've got 2 bromines attached, we can just go for the any combination of dibromo-propane. Okay, we've got 3 carbons, so we know it's going to be a propane. And really, we're looking at any combination of dibromo-propane. And you can, where can you put those bromines on dibromo-propane? Well, you could put them both on the same carbon, so you could have 1,1 dibromo-propane. You could have 1,2 dibromo-propane. Or you could have 1,3 dibromo-propane. And for those of you that don't get what the hell I'm on about, just draw it out. So you've got your 3 carbons. You're going to stick your bromines on. And here I've got 1,3 dibromo-propane. And of course, where else could you move those carbons? You could move them to the same carbon, so you could have 2,2 dibromo-propane. You can't have 3,3 dibromo-propane. That would just become 1,1 dibromo-propane. Remember, we have to give them the lowest possible numbering. But I could literally flip and move this bromine wherever I like. So I could move it there and it'd be 1,1 dibromo-propane. I could make it do some funny stuff. I think I better finish with that before it all goes a bit crazy. All right, guys, let's move on. You get the idea. Okay. Okay, question 4. This question is about gas volumes. TNT C7H5N3O6 is an explosive trinitrotoluene. Trinitrotoluene. Yeah, okay, whatever. C7H5N3O6 is an explosive because it can decompose very quickly and exothermically to form a large volume of gas. It's going to have a massive pressure increase and a lot of heat. An equation for this decomposition is 2 coefficient C7H5N3O6 solid decomposes to 3 nitrogen molecules in the gaseous form, 5 hydrogen molecules gaseous form, plus 12 carbon monoxides gaseous, plus 2 carbon molecules carbon solid. Calculate the volume of gas in meters cubed measured at 1250 degrees Celsius, 101,000 pascals, produced by the decomposition of 1 kilogram of TNT with an MR of 227. The gas constant for this question is R equals 8.31, and it's a 5 marker. So we've got a lovely question right here. So first of all, we should have spotted what equation we're going to use here. Got too many of these elements for it not to be this. We've got pressure and volume mentioned in the question. And we've been given the gas constant R and the temperature, so you know which one it is. It's PV equals NR. Now, what are we actually trying to find? We're trying to find V. V is the subject of the question right here, calculate the volume. So we want to rearrange that equation for a mark to show how we'd find V. And of course, we can do that by doing nRT. Let's bring our P underneath by dividing both sides by P. And then we're going to be left with P equals V. Now we need to go through and work out all the elements to put into that equation. So let's look at any one of these ones. We've got temperature, which of course is 1250 degrees. This is our temp. But what do we need to do? Temp has to be in Kelvin. So we're going to add 273. And what are we going to get? We're going to get 1523 Kelvin. So that's our temperature taken care of. We know what R is. It's always 8.31. We know that P has to be in pascals, not kilopascals. And actually, it's been done for us. So there's no conversion needed there. We've got pressure of 101,000. Now, so the tricky thing is to calculate the moles. That's going to be a little bit harder, the moles. We're going to need to do mass over MR. So we have 1 kilogram, which is our mass, and we need to divide that by the MR, mass over MR. Of course, we might as well convert the kilos to grams, because that's what our molecular mass will be in, divided by 227, and we should get the number of moles. So the number of moles of TNT anyway. And the number of moles of TNT is 4.41. So we've got 4.41 moles of TNT. Now we need to work out the total moles of the gas. So let's have a little look. How are we going to work out total moles of gas? Well, we are going to say we have... Okay, this is where we need to use the ratio. This bit's a little bit complex, and some people might make a mistake here and use the wrong number for N. If you use 4.41 for N, you'll only lose 1 out of 5 marks. That's the beauty of chemistry. You're going to get error carried forward. However, if you want to get this correct, we need the moles of gas over here on the right-hand side. Now, this shows us a ratio. I'm going to scribble over the writing of 2. So 3, 4, 5, 6, 7, 8. What is that? 22. However, we can discount the carbon because the carbon is solid. So that's not going to affect our pressure or volume. So we've got 3, 5, 6, 7, 8. We've got a ratio of 2 to 20. Let's simplify that. We have a ratio, therefore, of 1 to 10. So once this reaction has taken place and there's no TNT left, my moles are going to be times by 10. And so that means N is going to be 44.1. Now, that was the hardest bit of this question. And if you messed it up, it should only cost you 1 mark. So let's now get into it and plug the numbers in. 44.1, that's our moles, times 8.31, times 23. And we're then going to divide all of that by the pressure of 101, and this is going to give us our lovely jubbly answer, which should, if we round it to 3 significant figures, I always say if in doubt, round to 3 significant figures, unless they've told you otherwise, 5.52. So our volume of gas should be 5.52 meters cubed. Brilliant. They will accept a range from 5.5 to 5.53 meters cubed. So groovy, that's in that range. So we're up to 4.2. Alkenes have the general formula CnH2n. When alkenes undergo complete combustion, 1 mole of CnH2n reacts with 3n/2 moles of oxygen. Calculate the volume of oxygen needed for the complete combustion of 200 centimeter cubed of butane. The volumes of all gases are measured at the same temperature and pressure. And this is worth 1 mark. They want our volume of oxygen. Okay, let's go. So we've got, what is N first of all? Well, N, this is bute. Do you remember what bute stands for? It means that N equals 4 in this question. So N equals 4. We need to do 1 mole of bute. 1 mole of an alkene reacts with 3n/2 moles of oxygen. Let's work it out then. So we can use the 200. What is the volume? So we go times 3 times N, 3 times 4, We all know what that's going to be. That's going to be 12 over 2. So all we had to do here was plug in this, and we have our answer. 200 times 12 divided by 2, you're going to get 2,400 divided by 2, we're going to get 1,200 centimeters cubed. And if you mess that up, it was only 1 mark, a bit of mental maths there. 4.3, alkanes have the general formula CN H2N plus 2. This is another mathsy question, only worth a mark. Alkanes undergo complete combustion in a plentiful supply of oxygen. Define X in terms of N. So on the left-hand side, we have CnH2n plus 2 plus XO2, arrow, NCO2 plus bracket N plus 1, close bracket H2O. We want to define X, but we just want to define X in terms of N. Now, if we look at X, got X over here, and only the oxygen can be expressed in terms of X and N here, because the oxygen has X next to it, and then over here when it's in carbon dioxide and water, it's also got N next to it. So let's get rid of all the letters and write out those. So we have, how many oxygens are on the right over here? We have 2 oxygens, so we've got 2X equals, we've got 2 oxygens over here with this N, so equals 2N plus, we have N plus 1 oxygen over here, so N plus 1. I'm not writing the oxygens down, as we're just doing this as N and X. So this means that X equals 2N plus N plus 1. I'm going to divide both sides by 2 to get rid of this 2. And now we need to simplify on top here. And we're going to get X is equal to 3N plus 1 divided by 2. And that's our answer. And all of that hard work just for 1 mark. But there we go. That's chemistry for you. And just testing your basic math skills. All right. Let's look at question 5. This question is about the synthesis of propylamine CH3, CH2, CH2, NH2 by the reaction of 1-iodopropane CH3, CH2, CH2I with an excess of ammonia. Name and outline the mechanism for this reaction. We've got CH3, CH2, CH2I plus 2 ammonia molecules goes to CH3, CH2, CH2, NH2. Plus NH4I. That's for those of you that can't see. I'm just reading out the questions. You might not be looking at your phone right now. You might just be listening. So name and outline the mechanism for this reaction. Let's outline the mechanism and then we'll get to the name after. So the first thing to do here is draw your iodopropane. Now I want to draw it as mainly like a structural formula. And then I'm being lazy. You might want to draw the whole displayed version of this. I'm being incredibly lazy. You might want to display all the bonds here, but I don't fancy doing that. So I'm going to draw this here and this here. I'm only displaying the bit that I'm interested in. That is going to be reacting. And then I've got my I. So this is my iodopropane. Now my NH3 is going to approach. Now let's bear in mind that the NH3 always has a lone pair on it. Don't make the mistake of putting a minus. It doesn't have a negative charge, so don't put that. And once you see that lone pair on the NH3, that gives you an idea of the mechanism, because that lone pair is going to be attracted to something positive, and that something positive is going to be this carbon atom. And remember the halogen carbon bond here, this is delta positive, that carbon, so that lone pair is going to be donated over there, and that will then inform us about the name of this mechanism. What do we call a species that will donate a pair of electrons? And so that's a nucleophile. So we know that this is going to be nucleophilic. nucleophilic. I'll come to the second part of that name in a second. Now, obviously, carbon can't have 5 bonds, so it's going to get rid of one of these bonds. And this pair of electrons in that covalent bond are going to go to the iodine. So now let's draw what it looks like afterwards. So we're going to have an iodine molecule knocking about. I'll just draw that down here. Got a little iodine down here. And let's draw what it's going to become. So we're going to have CH3, CH2 again. This part isn't really getting involved, so I'm just drawing it like that. I've now got CH2 again, but we have, sticking off of this, I have our ammonia. Now, look at this nitrogen atom here. This is really important in these mechanisms. Nitrogen has 4 bonds around it. Now, when you find that situation, just like when you have NH4, you should remember from GCSE, this is the ammonium ion and has a positive charge spread across it. Exactly like this, whenever nitrogen has 4 bonds around it, we're going to put a positive charge there, okay? So this nitrogen's a little bit unstable like this, and so what's going to happen, we're going to get some further substitutions occurring. And what happens here is they told us up here, where is the excess? This word here, excess ammonia. This is key. This tells you that there's lots of ammonia knocking about. So another ammonia molecule comes in. Probably the biggest mistake students will make here is they'll take that lone pair and attack it to the positive nitrogen. That's a very understandable mistake, but that's not what happens. The lone pair goes to this hydrogen. I need to lengthen that bond. And then this hydrogen is the bond with the hydrogen and nitrogen. Hydrogen can only form 1 bond. It's going to donate these 2 electrons from that covalent bond back to the nitrogen and stabilize that molecule there. So this is what we've got going on here. And so when marking this, you really have got 4 arrows here, which are going to pick you up 4 of the marks. 1, 2, 3, 4. Now, some of them you'll need to have the you'll need to have the other things like the delta positive, delta negative, potentially. That's not a must, actually. That's not a must. The plus on the nitrogen is important. Otherwise, you won't get that mark there. Okay, super duper duper. Let's finish this name off. So nucleophilic, and what this is called is nucleophilic substitution, because when it's all said and done, the iodine is going to be, the iodine will have been swapped for that amine group, which is NH2. So it's nucleophilic substitution. Okay, 5.2. 1-iodopropane is a liquid at room temperature. Calculate the number of molecules in 5 centimeter cubed of 1-iodopropane with an MR of 169.9. Give your answer in standard form. For 1-iodopropane, density equals 1.75 grams per centimeter cube. The Avogadro constant with the symbol L is 6.022 times 10 to the 23 mole to the minus 1, and this is worth 2 marks. So what do we need to do here? Calculate the number of molecules in 5 centimeters of iodopropane. So first up, we want to look at maybe density equals mass divided by volume, because they've given us a volume and density. So in order to find the mass that we have, we want to rearrange to go mass is equal to D times V. So the density is 1.75, and we want to times that by the volume of 5, and that is going to give us 8.75 grams. So we now have the mass of 1-iodopropane. How many moles is that? Well, we're going to do 8.75 grams divided by the MR, which has kindly been given to us, is 169.9. And you're going to get an answer something which you can probably round, to be honest. 515, I mean, you could leave it as 0. You could round it to that if you wanted. It's up to you. Both the answers that result from either 0.0515 moles or 0.0520 moles will be in the range of acceptable answers. We now want to take that, which is the moles, so 0.0, I don't know, like if I stick 0.0520 in, times it by L. What is L? L is Avogadro's constant. So put that into your calculator, whack, whip, whop, and boom, 3.1 times 10 to the 22. That's how many molecules are in 5 centimeters of iodopropane. Super duper duper. 5.3, in an experiment, 10.3 grams of 1-iodopropane, MR169.9, thank you very much, are reacted with an excess of ammonia. 2.3 grams of propylamine, MR59, are produced. Calculate the percentage yield in this experiment. So what we need to do here is say, well, the iodopropane undergoing substitution with ammonia to form propylamine, very similar to the reaction we just did on 5.1, that mechanism, very similar. So it's a 1-to-1. You're going to get one amine group substituted for one iodine. So it's a 1-to-1 ratio, and that tells me that if we can work out the moles of one, we know the moles, expected moles of our product. So what have we got? We've got 10.3 grams. Again, very common. We're going to do mass over the MR, and this is going to give us the moles of iodopropane that we reacted with the excess ammonia, and that is going to equal 0.0606 moles. And what's that of? That's of the iodopropane. Okay, I can't bother to write iodopropane. It's just a long. Now, it's a 1-to-1. So I am expecting us to, in theory, achieve 0.0606 moles of bada bing, bada bang, propylamine. Now, we can times that by the MR to find out exactly how many grams that should be. So let's times by the MR of 59. And that will give us 3.58 grams. So our theoretical mass that we can achieve is 3.58 grams. How much did we actually achieve? So we're going to do actual mass, which was 2.3 grams. Oops. Easy with the caps. Oh, done it again. Get rid of the caps. And we want to put that over our theoretical mass. Excuse my theoretical, because that is spelt very badly. And we're going to divide that by 3.58 grams. Put a little divide line in there, please, Bob. And then we're going to times that by 100 to get the percentage yield. And that equals 64.3%. Boom. All right, moving on. Question 6. Trichlorofluoromethane, CCl3F, was developed as a refrigerant. This production and use of CCl3F is now restricted. The equation for a process used to manufacture CCl3F is, oh my good gosh, SBF3Br2 plus CCl4, arrow, CCl3F plus SBF2Br2Cl. Calculate the percentage atom economy for the production of CCl3F in this reaction. Give your answer to 3 significant figures. So that's going to be key. We're going to lose a mark if we don't use 3 significant figures. Okay. All you have to do here is add up your useful product, which is the CCl3F, add up the MR of that and divide it by the MR of both of the products. Okay, and if we do that and we put all those numbers together, we're going to get 137.5, We're going to divide that by 492.6, and that is, oh, we want to times 100 because it's a percentage, and that's going to give us roughly 27.9, and so 27.9%. Beautiful, beautiful, beautiful. Okay, let's move on. An alternative synthesis of CCl3F is the free radical substitution reaction between fluoromethane, CH3F, and chlorine. An intermediate in this alternative synthesis is dichlorofluoromethane, CHCl2F. Give equations to represent the two propagation steps in the conversion of CHCl2F into CCl3F. So we're looking for the propagation steps and not initiation. So initiation is when you start with a normal molecule and you end up with free radicals. With propagation steps, you want a free radical on the left in the reactants, and you also need a free radical on the right. So let's get to it. So first up, let's draw out our first propagation step. So CHCl2F, and we're converting it. How do I know to write that? It tells us here we're turning that into that, but we're achieving that over 2 steps. So we don't want to get there straight away. We need to get there in 2 steps. So what are we going to add? We're going to take our chlorine free radical that would have been made in an initiation reaction. Gosh, I can't speak. Right. Now what we need to do is create a free radical. And we're going to do that by removing the H. So let me zing off that H. That H is going to be snapped off, and we're going to get hydrochloric acid or hydrogen chloride, not really hydrochloric acid. We're going to get hydrogen chloride as a side product. And this is the free radical. Now, it's not necessary in AQA. I believe you can put the free radical symbol there, but it is better to put it here, really, to show it's on the carbon. But, you know, you can do it as you like. So now, how do I know how to start the next step? Well, I take the free radical formed in propagation step 1 and I move it down. So if you've got the first step right, you should get the start to the next step right, because you're going to bring the free radical down. Remember, we're aiming to get to this product here, CCl3F. So we know that's going to be on the right. We're aiming to get there in our second propagation step. And as it's a propagation step, we're also aiming to have a free radical at the end of it. So what's going to happen? This free radical is not going to, if I reacted it with another free radical, this would be a termination step. So I'm not reacting with another free radical. It's actually going to react with one of the chlorine molecules. And so what we're going to get here is CCl3 as the chlorine adds on and gets rid of that unpaired electron. So we're going to get CCl3F, and it's a propagation step. So we form yet another chlorine free radical, which of course can go back to propagation step 1 and start the whole process again. Brilliant. Point 3. Analysis of the products of this reaction shows the formation of a compound with the empirical formula CCl2F. Give an equation to represent a termination step forming this compound. Show the structural formula of the product in the equation. Got to do the structural formula of the product. That is not nice. Be easier if it was the molecular formula. So we're really looking, if we need something with this empirical formula. So let's just take 2 free radicals of that and join those 2 free radicals together. So we're going to do that as a free radical. And we're going to, you might say to me, how do you know that it's a free radical? There's no dot there. We'll count the number of atoms attached to this carbon. You know, if you've got carbon like that, what group is carbon in? Carbon's in group 4, so it must have an unpaired electron. Its other 3 electrons are all paired up here, bonded like that, but it's got an unpaired electron. That's why it's a free radical. So if you're wondering, how did he know it's a free radical? It's because of that, right? That's supposed to be Cl2F. Join these two together, and we're going to form, it's going to have the same empirical formula because we just doubled it for its molecular formula, but its empirical formula will remain the same. So, however, we've got to draw it in a structural formula. So if you think about this, it's going to be Cl2F, and then next to that is another carbon, Cl2 and F. And that's lovely jubbly. And if you're going, whoa, how can that be? Well, the 2 carbons are joined together. So what you're really doing is you're saying, oh my gosh, I don't know what's happened there with my pen. My pen just died on me. So what we're doing, this is where the free radicals were, remember, was over here. And now they've come together, the 2 free radicals. And all we're doing when we write this is expressing that. We're saying Cl2F joint to another Cl2F. And that is our structural formula. Beautiful. Of course, its molecular formula would be C2Cl4F2. And that has the same empirical formula as CCl2F, because we can simplify by dividing by 2. All right, enough waffle. Let's move on. So 7, in Europe, some of the glucose from crops is fermented to produce ethanol. Use of a carbon neutral fuel leads to no net emissions of carbon dioxide to the atmosphere. 7.1, the ethanol produced by fermentation of glucose may be regarded as a carbon neutral fuel. Justify this statement, include the relevant equations in your answer. Chemical equations, 4 marks. Basically, what we have to do here is write a couple of sentences, but we really want 3 equations that show that using crops or biofuels is carbon neutral. So the first step is to show that, look, 6 carbon dioxide molecules are taken in by photosynthesis and they form C6H12O6. Hopefully you will recognize that is glucose. And they form 6O2, which is oxygen. So here's our first one. Now, this is, I could write the answers if I wanted, but I'm going to just explain what this is. So this would be the language. Photosynthesis absorbs 6 CO2 molecules, right? So they're taken out of the atmosphere. That's good. What happens next? Well, we need to do fermentation, which is going to create our ethanol. So fermentation, you should know this equation off by heart. You take glucose. We have yeast as a catalyst. So I'm going to write yeast above the arrow. And that forms 2C2H5OH, 2 molecules of ethanol, plus 2 molecules of carbon dioxide. Now, yeah, that will do. That will do. Let's put the yeast down a bit. Right. So what does this show? This shows fermentation. Oh my gosh, got a bit excited with the caps. Releases 2 CO2. So right now, it's not carbon neutral. We've taken in 6. It's actually better for the environment than being carbon neutral. We've taken in 6 and we've only released 2 carbon dioxides. But of course, what are we going to do with the ethanol? Well, in a country like Brazil, they use biofuels like ethanol in the cars for combustion. So we're going to take that and we're going to burn that by combustion with 6O2. And that is going to become 4 carbon dioxides plus H2O. And what you can see here is combustion of ethanol releases 4 CO2. So just to highlight this, I've put the language in there, those sentences. I could have written all of that afterwards. So it's carbon neutral. And just to highlight that for you, let's pretend green is good. So 6 carbon dioxides have been taken in. by these three reactions. And then we want to show, look, fermentation gives out 2 and combustion gives out 4. So all in all, you have had a net production of 0 carbon dioxide. It's carbon neutral. Okay, let's move on. Coffee beans from South America are exported to Europe in an outer layer called silver skin. Okay, the waste silver skin can be fermented to produce a solution containing propanone, ethanol, and butanol. Suggests why ethanol produced in Europe using silver skin from South America is less likely to be carbon neutral than ethanol from crops grown in Europe. So what's the big difference with this here? Crops grown in Europe are likely to be carbon neutral rather than something coming all the way from South America. And it's quite simple. How does something from South America get to Europe? By transport, by ship, by plane, and they give out carbon dioxide. So we can just put transportation releases CO2. To be fair, even in Europe, when you do the photosynthesis and you grow the crops, there's going to be some harvesting of those crops before they can be fermented. And then there's going to be some transfer maybe of the ethanol to wherever it's going to be combusted in cars and stuff. So you're always going to, it's not, none of it is really carbon neutral, but this is going to be far less carbon neutral if you're moving the ethanol from another continent. Okay. Table 2 shows the enthalpies of combustion for 3 fuels from the fermentation of silver skin. So we've got ethanol, enthalpy of combustion minus 371. Butanol has a standard enthalpy of combustion of minus 2673. And propanone has a standard enthalpy of combustion of minus 786. How much energy is released per mole of carbon dioxide produced? Well, look, ethanol has 2 carbons in it. So the energy released per carbon dioxide molecule, we're just going to divide 1371 by 2, and that should give us 685.5. Now, there are 4 in butanol, and 1 molecule of butanol gives out minus 2673. So let's do minus 2673, divide it by 4. And if we divide that by 4, we should get 668.25. You could round it to 668. And then propanone is minus 1786. But of course, there's 3 carbons. So we're going to give out 3 carbon dioxides. So we're going to divide the total energy by 3 to find out how much energy is released per carbon dioxide. And it's going to be 595.33, or you could just leave it as 595. So now it says one way to measure a fuel's environmental impact is to measure the amount of energy released per mole of carbon dioxide produced. Complete table 2. Use your answers to deduce the fuel with the lowest environmental impact by this measure. Well, which one has got the lowest environmental impact? A lot of people might go for this. They say, oh, well, less energy is given out. Well, that's a bad thing, because if I'm burning propanone in a car, I'm getting less energy for each bad carbon dioxide molecule I release, or each harmful CO2. With ethanol, I'm getting a lot more energy for every CO2 released. So I'll have to burn less fuel to get the energy needed. So the best and least harmful is going to be, whoopsie, ethanol. As releases more energy per mole of CO2. So if you drive a car that is fueled with ethanol, and if you drive a car fueled with propanone, the same distance, you're going to burn more propanone and release more CO2 than you are ethanol, because ethanol gives you more energy for each mole. 7.4. A student investigated the combustion of propanone, C3H6O, using calorimetry. A copper calorimeter containing water was heated by complete combustion of some propanone. The student did not record the final temperature of the water. here are the results. Mass of propanone 1.18 grams, mass of water heated 260, initial temperature 22.3, the final temperature not recorded. Use the results in table 3 to calculate a value for the final temperature of the water in the experiment. Assume that no heat was lost in the experiment and that the heat capacity of the calorimeter is negligible. Therefore, propanone, the enthalpy of combustion, is minus 1786 kilojoule per mole. For water, the specific heat capacity is 4.18, and this is worth 4 marks. And we want our final temperature. Well, we're going to be using the equation where Q is energy released in joules is equal to the mass of water times the specific heat capacity times the temperature change. So we really need to find this temperature change. If we find the temperature change, we can add it to the initial temperature and get the final temperature. However, we have started off with 1 secondo. So I'm going to rearrange this to go Q over MC. If I do that, then I can get the final temperature change. So I need Q divided by the mass is 260 times the specific heat capacity of water, which is 4.18. Why am I using the mass of water? Here's a common mistake. Some students might put the mass of the fuel in there, but you've been given the specific heat capacity for water. So you need to be multiplying that by the water mass, not by the fuel mass. The fuel mass comes into when you want to find out how many moles you have. That's what you're doing that with. So Q over 260 times 4.18. Now what we need to do is reconvert this from minus 1786 kilojoule per mole. We need to get this just back into joules. So we need to get rid of the moles and then get rid of the kilojoules so that we just have it in joules. So, and then we'll know what Q is. So let's do that. So in order to find Q, boom, 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 we could first turn it into, let's go 1786 kilojoules, and I'm going to times it by moles. If I times it by moles, it's going to get rid of that and leave me with kilojoules. So how many moles have I got? I've got 1.18 grams. What's the MR of propanone? Have they given it to us? Oh, I've got to add up the MR of propanone. So propanone is going to look like this, guys. So and if you add that all up, hopefully it comes to 58 if I haven't made a mistake. By the way, I've not bothered drawing the hydrogens on. You just got to add those on. So 36 plus 6 plus 16. 36 plus 6 is 42 plus 16 is 58. That sounds good to me. That is going to give me that is going to give me 36.33 kilojoules. Now, I need to get rid of the K because Q doesn't have K in. Q is just joules. So I'm going to times 1000, and that's going to give me Q. This is getting all a bit complicated, isn't it? Oh my gosh, I'm running out of room here. So we're going to have 36,330 joules. That is Q. Let's whack that over the top of 260 times 4.18. Oh my gosh, my brain is not working properly at all today. Lick that into the calculator, and then we are going to get delta T, and delta T, geez Louise, I'm really trying here to squeeze this all in. Delta T is 33.4. That's our change in temp. Now we still got one more mark. We need to take the initial temperature, add that to the change in temperature, and that will give us our final temp. So 22.3 plus 33.4. So add that to 22.3, and we're going to get 55.7. And if you can follow that, you're a genius. So 7.5, butane 1-ol can be added to petrol for cars. An equation for the complete combustion of gaseous butane 1-ol is shown. C4H9OH gaseous plus 6O2 gaseous goes to 4 carbon dioxide plus 5H2O. Sorry, the enthalpy change is minus 2504. So it's exothermic, kilojoule per mole. We got some mean bond enthalpy data. Use these data to calculate a value for the mean bond enthalpy in gaseous butane 1-ol. So of the CC bond, you just want to write the number on that side, the number on that side, put a big fat minus between them, rearrange with an equals, and this rearrange, and Bob's your uncle, Jim's your aunt, and we're on the way. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, right, 9 CH bonds. So I want to do 9 times 412. And I want to do that because there's 9 CH bonds. If I didn't draw this out, I'd make a real cock up. Right. I've also got an OH bond right here, and the OH bond is 463. So I want to plus that to 463. I'm terrible at these. I always miss something, that there's a CO bond there. Probably going to miss that. That's 360. I'm hoping that is everything. No, we need the 6 oxygens. What is OO? OO for oxygen, O double bond O, is 496. So I also want to plus 6 times 496. And I'm going to whack that down into my equation down here. And when we zing-zang ziggling that, we get 7507. Now, let's not forget that we haven't included this, which the question is asking us for. This is why I had to draw it out. It wants us to find the enthalpy of one of these CC bonds. How many CC bonds are there? 3. If you just try and do it without drawing it out, you might see butanol and think 4 Cs. There's 4 CC bonds. There's 3. So we've got plus 3 CC, which we don't know what that is. Now, we need to subtract from that all of the bond enthalpies of the products. So let's get into that. I've got ooh, 805. So how many 805s have we got? If you think we've got carbon dioxide and we're going to times that by 4, what's that? That's 8 of those 805s. So I want to do 8 times 805. This is for the product number. And then if I look at H2O, I want to do 5 times this. That's 10. So I've got 5 waters. So I've got 2 HO bonds, and they're 463 each. So I want to do 10 times 463. And if we smash those together, we're going to get 11,070. And that is equal to, as we're told up top, minus 504. Sorry about the sound effects. I'm losing the will to live here. Right. So what I want to do is rearrange that to find that. Everybody does it in different ways. My brain is not a mathematician's brain, so I'll tell you the way I do it. Boom, boom, boom. I go, right, well, this number over here on the left must be smaller than this product number. How do I know that? My answer is exothermic. So I know that this minus 11,070 must be minus 2504, bigger than this side. So I'm going to go 11,070 and take that away, and that's going to tell me the energy of both of these. And when I do that, by doing 11,070 and I minus 2504. This is just my way. This is not the way proper mathematicians do it, but it's just my way of doing it. I get, for this side, 8566. So I know that's 8566. Now I can test it out. I can put into my calculator 8566 minus 11,070, and I will get minus 2504. So I know that's right. If we know that the butan 1-ol and the oxygen minus these bonds is 7507, then we can quickly work out what this is. We do 8566, take away 7507, and we're going to get 1059. Now there's 3 of these CC bonds, so don't forget to divide by 3, and that will give us 3, 5, 3. Ta-da! And that will score you 3 marks. I don't know where to put the ticks, but I would assume you get 1 mark for the 5. They're looking for some of these things like 11070. They're looking for you to divide by 3. You probably get a mark for 1059 and dividing by 3, but it's a total of 3 marks, and there's probably like 4 different things you can do to get 2 of the marks. Okay, we're nearly there, folks. We're nearly there. Butan 1-ol can be manufactured by reacting steam with but-1-ene in the presence of a catalyst, concentrated sulfuric acid. In the first part of this process, but-1-ene reacts with concentrated sulfuric acid to form compounds W over here and compound X over here. Butan 1-ol is then made from compound W. Name and outline a mechanism to show the conversion of but-1-ene into compound W in the first part of this process. So again, let's just smash straight into it. We've got but-1-ene, so let's outline the mechanism. Let's draw but-1-ene. Again, you can draw the bonds in between these if you really love it. I should attach the hydrogens. Let's attach the hydrogens. There's my double bond. That's my key area of interest. Hold on a minute, Bob. Got too many bonds going on there, mate. Right, clear that out. So, otherwise I have too many bonds, because remember there's a bond there. But yeah, I wasn't going to show that. Okay, where we've got a region of electron density here, and this is an alkene. You should know from alkenes, they love a bit of electrophilic addition. So I'm assuming this is going to be electrophilic addition. What happens here is this molecule, we've got our sulfuric acid, our catalyst, which at the end of it is going to come off, but our catalyst is attacking. So what on the catalyst is this going to want to go to? Well, it's going to want to go to a hydrogen, and our hydrogen, boom, boom, boom. Yeah, got another OH. Okay, can hydrogen have 2 bonds? Can this hydrogen be bonded here and bonded here? No, of course not. So we need to show the electrons going here. And this is going to leave this molecule looking like this with a lone pair and a minus. And that's going to be attached there. And we're just going to draw it exactly as it is, like that. Now what have we had happen here? We've had a carbocation form. And carbocations. Now we want to form W. So technically the carbocation could form on this carbon here, the 3rd carbon, or the 1st carbon, or the 2nd carbon, however you want to word it, or 3rd or 4th. But we've been told that it is forming over here. So this is our carbocation. And I just need to stick my hydrogens on there. So that is going to attack there. Lovely jubbly. That double bond is going to go to that carbocation. And the name of this is electrophilic addition. Beautiful. 1 mark for the mechanism. 1 mark for the arrow for the double bond to the H. 1 mark for the H coming over to the O. 1 mark for your carbocation intermediate product. You need the lone pair and the minus and the arrow. 7.7, there is a very low yield of butan 1-ol from butan 1-ene in this manufacturing process. Explain why. Right, I'm going to draw a little diagram out. You should know this. This is, now there's 2 possible carbocations that can form here. So I just want to show you for the reaction. And what this is essentially saying is, why is it that this right-hand one over here, why does this one end up being the minor product? And why is this one the major product. And hopefully you know by now, and if you don't, then if you don't know, then get to know. You have an R group here. You have an ethyl group here attached. So we've got two lovely R groups. What are R groups? R groups are electron donating. They kind of let their electrons hang out very close to this carbocation, and they stabilize that positive charge, making it a more stable molecule. So that butan 1-ene would rather form that carbocation. Why doesn't it want to form this one? Because if we do this, it's got a propyl group attached, and that is it. These others are hydrogens, they don't count. So it's got one R group, a propyl group. It's better to say alkyl groups than R groups. Anyway, so how do we put that into words? So I just want to say like butan 1-ol formed from a less stable carbocation. More stable carbocation favors formation of but 2-ol, okay, as more alkyl groups attached. So it's the carbocation with the most alkyl groups attached that forms. Okay, section B, this is the multiple choice. Answer all the questions in this section. Only one answer per question is allowed. For each answer, completely fill in the circle alongside the appropriate answer. That's the correct method, little circle filled in. If you want to change or cross out your answer, that means your answer's wrong. If you then go back and have triple second quadruple thoughts and think, oh, that one's right, you circle it like that. Okay, let's go. Question 8. When hexadecane, C16H34, is heated to a high temperature, one molecule of hexadecane decomposes to form an alkane containing 8 carbon atoms and 2 different unsaturated compounds. Which equation could represent this reaction? So let's go through and check them all out. Okay, let's look at this first one here. So we're told that we should get an alkane formed. Well, we have an alkane there, C5H12. How do I know it's an alkane? Remember that for alkanes, CnH2n plus 2. So I definitely need something that fits that. And then we've got some unsaturated hydrocarbons. So I need 2 products that fit this general formula. So that is an alkane, that is an alkene, and that is an alkene. All good so far. However, you'll notice we have 34 carbons here and 16 carbons here. What have we got? C8H16, C5H12. Oh, actually, the alkane is supposed to contain 8 carbon atoms, and this one is an alkene with 8 carbon atoms. It says alkane with 8 carbon atoms. The 8 carbon product here, C8H16, is an alkene. That's wrong. Okay, let's look at B. C16H34, we've got an alkane containing 8 carbon atoms, C8H18. That's good. However, we have C6H10 and C2H6. We have another alkane. There's 2 alkanes there. C2H6 is ethane, and it told us that we have 1 alkane and 2 unsaturated. So this is incorrect. C16H34 again, there's our alkane, octane, C8H18. Then we've got 2 ethene molecules, and we have C4H8, which is butene. So this sounds pretty good. 2 different unsaturated compounds, ethene and butene. This is the correct answer. There we go. All right, let's move on. Clear that, clear that. Question 9. The diagram shows a fractionating column used in the industrial fractional distillation of crude oil. We got gases at the top: petrol, naphtha, kerosene, diesel oil, lubricating oil, fuel oil, and then residue going down the fractionating column. We have a furnace, boiler heater kind of thing, with crude oil coming in and getting vaporized. Which statement is correct? A, the most viscous product is fuel oil. Viscous means thick. Well, residue is going to be thicker as it comes out below fuel oil. So that is not correct. Let's look at the next statement. The boiling point of naphtha is higher than diesel oil. Well, no, naphtha's higher up. The boiling points decrease as you go up, and naphtha is two places above diesel oil. So that is another incorrect statement. Let's check the next statement. Molecules in diesel oil are held together by hydrogen bonds. Actually, the molecules inside crude oil are not held together by hydrogen bonds. It's van der Waals forces that are holding these guys together. So that is incorrect. And then kerosene is a mixture of compounds. Now, even if you didn't know that is true, it's the only answer left. But yes, kerosene is a mixture of different alkanes. Okay. 10. Which statement about polyethylene is correct? So it has a lower relative molecular mass than ethene. Well, ethene's the monomer, so surely the polymer will have a bigger molecular mass. So that must be incorrect. It has a lower density than ethene at standard. Why would it have a lower density? They've been compressed under pressure, so this is going to be incorrect. Monomers are actually squished together under pressure when you do a polymerization reaction, so they're going to have a higher density. C, it has, and also another thing, it's a plastics. Polyethylene is a plastic, ethene is going to be a gas, so you can see straight away it's going to have a higher density. Has a higher melting point than ethene. Well, that would be true, because of course ethene is a much smaller molecule than polyethylene, so those van der Waals forces or intermolecular forces are going to be stronger in polyethylene than ethene. So that's our correct answer. And it doesn't decolorize bromine water because there are no double bonds in polyethylene. Okay. 11. A polymer is formed when the monomer CH2 double bond CHCN is formed from that monomer. Which statement is not correct? You always have to check these. I always miss these. So which statement is not correct? We're looking at what is incorrect. So I'm going to start tactically from the bottom here. The polymer has this repeat unit. When you check that out, when you're making a repeat unit, you want to get rid of the double bond, which they've done here. You want to open up the ends. And essentially, that's what they've done. So that's actually correct. The polymer is an addition polymer. When you've got a unsaturated compound, which is the monomer, it undergoes addition, polymerization. The monomer is unsaturated. Well, we can see that there. Yes, it's unsaturated. It's got a double bond there. So yeah, the monomer is propane nitrile. Do you spot the mistake? There's a double bond there. Propane suggests a saturated compound. It should be propene. So this is the correct answer in that this is the incorrect statement. So that's the correct answer. Let's look at 12. Which alcohol, when dehydrated, forms a mixture of alkenes? So, well, it's going to have to be, it can't be these. It can't be propan 1-ol, and it can't be propan 2-ol. Why, you ask? Well, look, check it now. If I've got propan 2-ol and it forms a double bond there, that's going to be the same alkene as if it forms a double bond there. So it makes no difference. It can't do this. It's always going to end up being prop-1-ene. However, pent 2-ol can, because the hydroxide group is going to be in the middle with pent, and therefore it can form like pent 2-ene, pent 3-ene. So yeah, it's pent 2-ol. Okay. Let's check out 13. Which compound has the highest boiling point? So what I want to do is zing down through them and write down what they've got. So we've got a carbonyl group here. You know the old C double O, and that is going to have delta negative, delta positive. That's going to be a polar bond there, and we're going to get dipole permanent dipole forces there. So I'm going to have dipole forces. Also, I need to get a rough idea of its size because that's going to give me an idea of how strong its van der Waals forces are. So it's got an MR of 72. So it gives me an idea roughly of the electrons. And then I've got this is got an MR of 74 if you add them all up. And it's got an OH. So that is going to have hydrogen bonding. So B's got a bigger mass, so stronger van der Waals forces, and it has hydrogen bonding. And hydrogen bonding, of course, is the strongest intermolecular force, is stronger than those dipole forces. Over here, we've got dipole and 72, so it's going to be very similar. And then down here, I've got no hydrogen bonding, no dipoles. I've literally just got van der Waals forces, and it's also got an MR of 72. So over here, it's going to be hydrogen bonding, strongest intermolecular force, and this has stronger van der Waals forces. Great. (14) Which statement about molecules in a gas is correct? A, at a fixed temperature, they all move at the same speed. Excuse me, peoples. Well, that's not going to be true because in any gas, they're moving at different speeds. They're moving randomly and at different speeds. So that's not true. At a fixed temperature, their average kinetic energy is constant. Well, that is true. Temperature is actually a measure of the mean kinetic energy of the particles. So as temperature increases, there are more molecules with the most probable energy. No. As temperature decreases, there are fewer molecules with the mean energy. 15. Which compound produces CH3 CHCO CH3 when oxidized? So let's draw this compound out, and then we'll get a good idea. So we've got CC. That is so terrible, my drawings. Let's go. Boom, boom, boom. Now, we have a methyl group that is coming off over here. So, okay. So basically, what's that called? Have I done the right amount of carbons? 1, 2, 3. Oh, I should have one there, right? Yeah. 1, 2, 3, 4. 1, 2, 3, 4. Okay, cool. Should be hydrogens on the end of that. But essentially, we're looking, the main chain has 4 carbons in it. So we're looking at bute. So let's get rid of anything that's not bute. Oxidized is going to become an alcohol. So it's either going to be 2-methyl-butan-2-ol or 3-methyl-butan-2-ol. Well, it can't be 2-methyl-butan-2-ol because the methyl group is on a different carbon than the ketone, which is where the OH will form. So if you're wondering why that's an ol, that is going to be oxidized to be OH. So the answer is going to be 3-methyl there, butan, and then 2-ol. Lovely bubbly. Where's my pen? There it is. Okay. 16. Which reaction does not result in a change in the shape around a carbon atom? So which one do we not get a change in shape? So chloromethane with aqueous sodium hydroxide, that is going to go from, let's just check this one out. We got chloromethane like that. And then that is going to become OH, boom, boom, boom. Yeah, they're both going to have the same shape, some sort of a tetrahedral or whatever the hell that is. So they're going to have the same shape. There's no significant difference there. If we go ethene with bromine, we're going to go from that double bond to 1,2-dibromethane. Propane with excess oxygen, we're going to get carbon dioxide and water, I guess. Propan 1-ol with acidified potassium dichromate. We're going to go all the way to carboxylic acid or aldehyde, blah, 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 blah. Right. Lovely. Which compound has the same empirical and molecular formula? So this means, yeah, Let's check them out. Okay, can I simplify that? Yes, I can. I can do that to C2H5. So not that one. Beep, beep. Butanene is same as butene, is going to be C4H8. Simplify that to C2. Oh no, we can simplify that to CH2, can't we? Lovely bubbly. Propane, C3H8. Can we simplify that? No. So the answer is propane. Propene, of course, we could simplify this one. We could do CH3 by dividing both by 2. So the answer is propane. Right. Methanol is made in this equilibrium reaction using a catalyst. So carbon monoxide plus 2 hydrogen molecules, reversible symbol, goes to methanol. It is exothermic, minus 91 kilojoule per mole. The reaction reaches equilibrium in a container of a fixed volume, which is the expression for Kc. So we don't need to worry about the volume. Or you just want to do product, big bad boy P over the reactants. So you're looking at products over the reactants. So CH3OH over the reactants. And you need to make sure that there is a 2 outside the concentration square brackets for the hydrogen. So there we go. What's the difference between A and B? My eyes cannot pick it up. Well. Ah, there's a plus sign. It's times, remember? Shouldn't be a plus sign. Okay, fair enough. Couldn't spot that. Took me a little while. Right, we're on to the last one. Last page, 19. 2 moles of carbon dioxide is mixed with 3 moles of hydrogen and allowed to reach equilibrium. The equilibrium mixture contains 0.6 moles of methanol. What is the total amount in moles of gas at equilibrium? Right, different people do this in different ways. I'm going to show you one of the ways to do it. So some people like the ice method. So you write ice down the side. Let's do, what was it? Carbon monoxide plus hydrogen allowed to reach equilibrium and becomes methanol. What is methanol? CH3OH. So I need 2 lots of hydrogen. Right. So at on initial, we have 2 moles of this, 3 moles of that. That I there stands for initial. So 2 moles of that, 3 moles of that. We're going to have 0 at the start. Now, what's the change? Well, it says the equilibrium mixture contains 0.6 of methanol. So I can come down here and I can write 0.6 because this E here stands for equilibrium. Now, by how much did each one change? Well, there's a ratio of 2. If you want to work out, if you want to work out the change, I'm going to multiply that by the ratio number. So 0.6 times 2, this one changed by 1.2. Okay, because I needed 1.2 because it's a ratio of 2 to 1. So that left me with 1.8 of hydrogen. And then this is a 1 to 1. So the amount, this changed by 0.6. So this changed by 0.6. And that means that I have 1.4 left. So at equilibrium, I have 1.4 and 1.8 is 3.2 plus 0.6. I should have 3.8 moles. And the answer is B. Booyaka. Right, going a bit crazy now. Question 20. Which change in condition will decrease the equilibrium yield of methanol? So which one is going to force the reaction back this way? If we increase the amount of CO in the equilibrium, if I make more carbon monoxide, Le Chatelier says it's going to do the opposite. So it's going to move over to the methanol. So that's definitely not going to decrease the equilibrium mixture. If I increase the pressure, it's going to go to the side with the least gas molecules, which is the right-hand side. So that is not going to work either. That is increasing the pressure is not going to decrease the yield. It's going to increase the yield, increase the surface area of the catalyst. Well, if I increase the surface area of the catalyst, it won't affect the yield. It will increase the reaction rate, but remember, catalysts do not affect yield. And then if we increase the temperature, we'd have to know, but if I increase the temperature, yeah, booyaka. So it's an exothermic reaction on the other page. I think it said it was minus 91 kilojoule per mole, and the minus enthalpy change tells me just before question 18, tells me that if we increase the temperature, it's going to force it into the endothermic side, which will be back to make the carbon monoxide and the hydrogen. So that will decrease the yield. Right, last two questions. 21. When 2-bromobutane is warmed with potassium hydroxide, substitution and elimination occur. Which of these compounds is not produced? So, well, if it's 2-bromobutane, you're not going to get butan-1-ol, are you? No, you're not going to get butan-1-ol. So that's not going to be produced because the bromo's on the second. So that's where the OH is. Yeah, you get the idea. What is the role of the hydroxide ions in the elimination reaction? Well, this is probably the biggest mistake people will make here is the hydroxide ions, they will say, are a nucleophile, because they are in many reactions, but not this one. In this reaction, it's base elimination. So we've got, it's a base. And that's it. That's your lot there. So boom. Why is it a base? The hydroxide ions accept a hydrogen to form water and create that double bond. Okay, let's go.
You're still here? It's over.